Hi, and welcome to our next session here on mutual information. So the second session on mutual information. So here I'll discuss, basically more properties of mutual information and compare this also to measures of linear dependence like the Pearson correlation. Okay, so first bunch of properties with associated proofs. So first of all, mutual information is always non-negative, so it's bounded from below by 0, and it's exactly 0 if and only if x and y are independent. Is that easy to prove? Yes, because we already know this basic equality here between mutual information and Kullback-Leibler, between the joint and the product of the marginals. And we already know that Kullback-Leibler is non-negative, so mutual information is also non-negative. And we also know that this relationship here in Kullback-Leibler holds with equality if and only if the joint is the same as the product between the marginals, and that is only true if and only if x and y are independent, and this is exactly what we want to have and what we need. Next thing, the next very intuitive and plausible property is that conditioning reduces the entropy, so getting more information cannot hurt. So if we compare the conditional entropy of x given y and we compare that to the unconditional entropy of x, the former is bounded from above by the latter. So the unconditional entropy of x is always larger than, or the very most equal to, the conditional entropy when we condition x on y. And again, this relationship here holds with equality if and only if x and y are independent. Is that easy to prove? Well, yes, in a certain sense it's again a one-liner. So we can actually take a look at the difference here between eta of x and eta of x given y. And we already know from the previous session that this is the same as mutual information. We now know that mutual information is non-negative, so it immediately follows that this relationship here holds. Okay. This is quite nice. Actually, have we also shown that this relationship holds if and only if x and y are independent? I guess maybe I should have added 3 words about this here on the slide, but it's actually very obvious. So let's assume that x and y are independent. Well, then this thing here, the conditional entropy, and we've discussed before that this is then simply eta of x, so then they are the same. If the conditional is the same as the unconditional, then we know that this difference here must be 0, which means mutual information is 0. And if mutual information is 0, and we've just discussed here in this theorem that then x and y must be independent. There's a further very nice bound on entropy, so on general multivariate entropy, which we have here. We can bound that from above through the sums over all the univariate entropies of x1 to xn. And again, this relationship holds with equality if and only if all of the xi are jointly independent. Can we easily prove that? So instance, again, it's a one-liner, so we can now use our chain rule that we've already shown, and we can use this conditioning reduces entropy law from the slide before. So we can start with the joint multivariate entropy, eta of x1 to xn. We can write that down through the chain rule, and then we can bound each individual term by that law here. So we have all of these eta of xi's in the sum on the right-hand side. And equality holds if and only if xi is independent of all of the other variables which come in the sequence before. So if xi is independent of xi I minus 1 to xi, and that holds for every I. And if that holds for every I, that basically means that exactly means that all of the xi's are jointly independent. For this, if this is not immediately clear to you, this might need a couple of more lines. Again, write this down. This is a nice test to check your understanding of things. Okay, so let's wrap this up a little bit. Let's put this a bit more in context. So mutual information is apparently a measure of the amount of dependence between variables. That's pretty great. So we now have a further alternative measure of dependence between random variables, and it's very nice that it is 0 if and only if our random variables are stochastically independent. On the other hand, if one of the random variables is a deterministic function of the other, then mutual information is maximal. So it's exactly the entropy of the first random variable that also is, I don't know, quite good, quite plausible. Unlike Pearson correlation, mutual information is not limited to real-valued random variables, so we can use that on categorical stuff and we can use that on continuous stuff. Because it nicely measures dependence between random variables, mutual information can also be used as a feature filter in feature selection, and I'm actually discussing that in our chapter on feature selection and feature filters, and sometimes there it's also called information gain, but that's just terminology. It can also be used in classification and regression trees to select features when we search for the optimal split, so as a split criterion. If you then split on mutual information or on information gain, this is exactly the same as splitting with risk reduction and log loss, and I actually proved that in our chapter on decision trees. There's a further, a little bit more complicated property of mutual information, which states that mutual information is actually invariant under injective and continuously differentiable reparameterizations, which is also a pretty nice property of MI. And there's a deep dive online on our webpage where we prove exactly that statement formally, so you can go through all of the details there. But it's a little bit more technical, and we've banished this into a separate slide set. Let's compare mutual information now a little bit more to correlation. So let's remind ourselves how correlation works. So if two random variables are independent, then we should remember that their correlation is 0. But if two random variables, if two random variables have a correlation of 0, then they don't necessarily have to be independent. And this is because correlation only measures linear dependence and not general dependence. So the other direction of the statement, so if two random variables have 0 correlation, and this implies that they are independent, this would assume our knowledge of the bivariate distribution of x and y being actually Gaussian, being normal. If we know that, then it's if and only if. Then correlation equals 0 is exactly equivalent to the two random variables being independent. But in general, under non-Gaussian bivariate distribution, this second direction does not hold. And in order to visualize this, we've produced these pretty standard cases of two variables being pretty strongly dependent and in various shapes and forms. So this is not a completely deterministic but very strong dependence of y being a stochastic function of x, which gives rise here to this double W shape. So it's obviously not a linear relationship, and there's a bunch of other cases, and you can see that for all of these cases the correlation is nearly 0, although there's a very strong dependence between the two random variables. But fortunately, at least mutual information for all of these cases is quite large, and the stronger the dependence is, the larger mutual information is. So we can actually now see mutual information as a more general and maybe a more, nicely well-behaved, not sure whether I want to say useful, it's more general measure of dependence between two random variables, because it also measures nonlinear dependence between random variables. I want to wrap that up with another very, simple example here, which is also quite nice to remember and to use in some calculations. So let's now take a look at two correlated Gaussian random variables. So we have x and y, and they're supposed to be Gaussian, zero mean, and they have a covariance matrix K. I guess I could have also called this capital sigma. And I'm writing that down in the standard form when I talk about the correlation between the two random variables. So I write that down in terms of sigma squared. So apparently I'm assuming that the marginals of x and y have the same variance, sigma squared, and then there's a correlation rho between x and y. Okay, so this is my parameterized covariance matrix here, capital K. And what I now can do is I can write down the differential entropy of x and y, which is given here by this formula. And this we have actually already discussed and calculated and derived before. We even discussed how we can compute the differential entropy of a bivariate distribution, a bivariate Gaussian, and derive this formula here, which I can now also write like that when I plug in the determinant of capital K. So the determinant of my covariance matrix, so of this guy, so this is actually, let's just do that. So this, I just have to go over the diagonals, right? So this is sigma squared times sigma squared minus rho sigma squared times rho sigma squared, which is rho squared times sigma to the fourth power, which is exactly what we have here. Yeah, so just factoring out the sigma to the fourth power. Okay, so what we can now do to get our hands on the mutual information between x and y, which we want to compute, is we can use this formula here. So this is the differential entropy of x plus the differential entropy of y minus the differential entropy of x comma y. So just plug in all of the formulas that we just noted down. We simplify things a little bit, and then we get this nice little formula here. So this is minus 1/2 times log of 1 minus rho squared. We can now check a couple of cases. So what happens with this formula if a correlation is 0? If correlation is 0, then x and y are actually independent because their joint distribution is Gaussian. And then mutual information is 0. So we already knew that. If x and y are independent, their mutual information must be 0. But fortunately, the same fact is also expressed here by this formula because log of 1 is actually 0. If we have maximal correlation, so if our correlation is either positive +1 or negative -1, then x and y would be perfectly correlated, and then we would have log of 0 and mutual information would go to infinity. Okay, this wraps up this session. See you in the next one.